This machine can spot chaos without predicting where the system will go. Watch, two dots begin so close together they look like one. After a few swings through this double pendulum map, they tear apart. The machine catches that instability immediately, then does something almost rude. It pushes the dots back together and repeats the experiment. Stretch, measure, reset, stretch again. From those tiny local measurements, it produces one number. Positive means chaos. Negative means nearby futures collapse toward each other. 0 means they mostly keep pace. And here's the part that got me. The machine never needs to follow the second dot long enough for the two paths to become visibly different. It keeps destroying the dramatic evidence. Every time the separation grows, it shrinks the separation back down before continuing. Somehow that repeated act of forgetting preserves exactly the information we care about. So we can take a complicated system, trace one ordinary trajectory through it, and diagnose whether its future is fragile without successfully forecasting that future. That sounds contradictory. If chaos means prediction fails, what information is left for a prediction machine to use? The answer is hidden in the very first instant when two futures begin to disagree. While their separation is still tiny enough to obey a much simpler rule, we are going to build that rule directly on the moving system. One arrow attached to one trajectory, stretch one step at a time, and once that arrow starts reporting its measurements, the mess turns into arithmetic. The missing information lives in that tiny arrow. Call the system's current state x. For a swinging pendulum, x might store angle and angular velocity. For a weather model, it could contain millions of temperatures, pressures, and wind speeds. Now, make a nearby copy whose state is x plus a very small arrow delta x. After one time step, the original state moves somewhere new, and the nearby copy moves somewhere slightly different. Their new separation is what we measure. While delta x is tiny, the system acts almost like a linear machine on that arrow. It can rotate it, shear it, shrink it, or stretch it. The curved global dynamics briefly become a little parallelogram problem. Gorgeous. The matrix describing that local action is the Jacobian. Each entry asks a concrete question. If I nudge this input coordinate, how much does that output coordinate change after one step? We do not need to stare at the whole matrix yet. Visually, it takes a tiny circle of possible errors around x and turns it into an ellipse around the next state. The ellipse's long direction is the most amplified uncertainty for that step. So why not measure that longest direction once and declare victory? Because the trajectory moves. At the next point, the local stretching directions change. A direction that grows here may rotate straight into a contracting direction later. Chaos is a long argument assembled from short, changing pieces. We need to carry one arrow through all of them. That creates a problem though. If the system really is chaotic, the arrow soon grows so large that our lovely linear approximation stops being true. So the reset is what keeps the calculation honest. Suppose the arrow begins with length epsilon. We advance the trajectory one step and let the Jacobian transform the arrow. Maybe its new length is 1.4 epsilon. We record 1.4, then divide the arrow by 1.4 so its length returns to epsilon. Its direction stays exactly where the dynamics sent it. That last detail is easy to miss. We erase the dangerous size while keeping the learned direction. Next step, perhaps the arrow shrinks to 0.8 epsilon. Record 0.8 epsilon. Record 0.8, reset, then 1.1, then 1.7, and onward. Multiplying all those factors reconstructs the total growth our arrow would have experienced inside the linear model. But products become awkward very quickly. 10 modest stretches can make a huge number, and 10 contractions can bury one near zero. Logs clean this up. The log of a product is a sum, so we add log 1.4, log 0.8, log 1.1, log 1.7, then divide by the elapsed time. That running average is our estimate of the largest Lyapunov exponent. Positive means exponential growth on average. A value of 0.2 per second says a tiny error grows roughly like e to the power 0.2 t. Its doubling time is log 2 divided by 0.2, about 3.5 seconds. Now the reset trick looks less mysterious. The lost length is sitting safely in the ledger. The arrow can stay tiny forever while the ledger remembers decades of growth. There's still a suspicious choice buried in this machine. We started with one arbitrary direction. Why should that arrow discover the direction that matters most? An arbitrary arrow works because repeated stretching selects its own direction. Here is the cleanest version. Imagine every step applies the same linear transformation. One special axis doubles lengths. A perpendicular axis halves them. Start the arrow almost anywhere. It has some component along the doubling axis and some along the halving axis. After one step, the first component doubles while the second is cut in half. After several steps, the shrinking component becomes negligible and the arrow lines up with the expanding axis. The only losing choice is an arrow exactly on the contracting axis, and the tiniest numerical disturbance knocks it off. A changing nonlinear system is messier because its preferred direction moves along the trajectory. Still, the same competition happens continuously. Directions with slower long-term growth fade relative to the fastest one. The reset preserves orientation, so the arrow gradually locks onto the dominant stretching history. This is basically the power method from linear algebra, except the matrix changes every step and the answer belongs to an entire orbit. Let it run through an initial settling period, and the choice of starting arrow usually stops mattering. Now we can test the machine on 3 systems. A stable fixed point drags every nearby state inward, giving a negative exponent. A steady rotation keeps separations roughly unchanged, giving 0. A chaotic map repeatedly folds its space while stretching one direction, giving a positive exponent. Wait, folding has not appeared in our measurement at all. Our arrow only knows about stretching. Yet bounded chaos cannot stretch forever without leaving the available region. Something has to bring the motion back. That missing operation explains why chaos can remain trapped on a finite screen. The fold keeps the chaos in the box. Take the Baker's map, a wonderfully blunt model of this whole idea. Start with a square. Stretch it horizontally to twice its width, squeeze it vertically to half its height, cut the result, and stack the right half on top of the left. Like dough, if your bakery has unusually strict coordinates. Every step doubles small horizontal separations, so the Lyapunov exponent in that direction is log 2 per iteration. At the same time, the stacking returns everything to the original square. Stretching creates sensitivity. Folding keeps the trajectories bounded and mixes distant pieces together. Our little arrow measures the smooth stretching between folds. If 2 points land on opposite sides of a cut, their visible separation can jump, which looks awkward for a derivative. That is a boundary issue in this idealized map. Smooth chaotic systems perform the same basic maneuver with bending instead of a sharp cut. Now watch what happens to 4 binary digits encoded in a point's horizontal position. Each iteration shifts the binary expansion left. The leading digit determines which half of the square the point enters, then that digit gets moved into the vertical stacking history. A tiny unknown digit far down the expansion marches forward until it controls a large-scale choice. This is sensitivity made mechanical. The future restored in the fine detail of the initial condition, and the map steadily promotes that detail into view. Our exponent says how fast that promotion happens, but one positive average can hide a lot. A trajectory may contract for 20 steps, burst apart for 3, then contract again. If we only report the final average, we miss when predictability actually fails. That hidden variation is why finite-time Lyapunov exponents are so useful. Instead of averaging from the beginning of time, choose a moving window. Over the next 10 steps, how much does the arrow grow? Slide the window forward and calculate again. Now chaos gets a weather report. Calm region here, violent burst there. A ridge where nearby states become especially fragile. On a map of starting positions, color each point by its finite-time exponent. The bright ridges often trace invisible transport barriers, curves that organize where material can and cannot travel. Drop dye on opposite sides of one ridge in a flowing fluid, and the colors may separate even though the velocity field looks smooth. This is the machine doing more than stamping a whole system chaotic. It tells us where and when uncertainty is being manufactured. There is a price. The answer depends on the window length. Too short and we mostly see local quirks. Too long and sharp events smear into an average. It can also depend on direction and on the coordinates used to measure distance, especially over finite intervals. So this is a diagnostic, not an oracle. It measures the growth of infinitesimal errors along a chosen trajectory under a chosen model. Model errors, noisy observations, and rare jumps are additional trouble. Math remains stubbornly specific, which I appreciate even when it ruins the sales pitch. There is one more upgrade. One arrow reveals only the fastest growing direction. A high-dimensional system may stretch along several independent directions while crushing others. To read that whole geometry, the machine needs a bundle of arrows, and those arrows immediately try to collapse onto the same winner. To stop every arrow from chasing the same direction, we repeatedly make them perpendicular again. Start with a small orthogonal frame. Advance all the arrows through the local Jacobian. They stretch and tilt into a skewed bundle. Measure how much genuinely new length each arrow contributes, then rebuild an orthogonal frame pointing through the same nested spaces. This is the QR algorithm. The first recorded factor tracks the strongest direction. The second tracks growth after removing anything already explained by the first. Continue, and the long-term averages give the full Lyapunov spectrum. Several positive exponents mean several independent ways for errors to explode. Negative ones mark contracting directions. 0 often belongs to motion along a continuous trajectory, where shifting slightly forward in time neither grows nor disappears, and the sum tells us how tiny volumes behave. If the sum is negative, a cloud of possible states loses volume overall, even while one direction stretches. That combination is the geometry behind a strange attractor. Pull apart here, crush harder elsewhere, fold, repeat. A whole cloud becomes a filament, then layers of filaments, confined to a shape with fine structure at every scale. This is the answer the opening machine was guarding. It predicts chaos without predicting the future because those are different jobs. Forecasting asks where the dot will be. A Lyapunov calculation asks how rapidly nearby answers stop agreeing. The first can fail spectacularly while the second converges to a stable number. And yes, I love that the machine succeeds by resetting its evidence over and over. It forgets the arrow's size, writes down the loss, and carries only the direction forward. One stretch at a time, it measures exactly how a future becomes unknowable.